Welcome back! We have spent the series so far on single vectors and the geometry of one line or one plane. Today we ask several constraints to hold at the same time, and that question, how do straight constraints combine, is the gateway to everything that follows in linear algebra. We will start by pinning down exactly what makes an equation linear, a clean weighted sum of unknowns with nothing curved. Then we look at the geometry, where each equation is a line or a plane, and solving the system means finding where they all meet. That picture leads to a surprisingly rigid fact. A linear system can only ever have 0, 1, or infinitely many solutions. We then learn to compress a whole system into one elegant matrix statement, A times X equals B. And finally, we strip it down to its raw numbers, the augmented matrix, which is the object the next episode learns to solve mechanically. Let's begin. First, what does linear actually mean? A linear equation in the unknowns x1 through xn looks like this: a 1 times x1 plus a 2 times x2 and so on, all set equal to a constant b. The numbers a1, a2, and so forth are the coefficients, and they, along with b, are fixed constants. The defining feature is that every unknown appears to the first power and is multiplied only by a constant. So 3x minus 2y plus z equals 7 is linear, and so is x1 plus x2 equals 0. What is not allowed? Any curving. And x squared is out. A product of two unknowns like x times y is out. A sine of x, or 1 over x, is out. The moment an unknown is squared, multiplied by another unknown, or fed into a function, the equation stops being linear. Keep it to constants times unknowns, added together, equal to a number. That flatness is exactly what makes these systems so beautifully solvable. Now the geometry, because it explains everything. A single linear equation describes a single flat object. In the plane, an equation like ax plus by equals c is a line. In space, ax plus by plus cz equals d is a plane. A solution to a whole system has to satisfy every equation at once, which means it must lie on every one of those lines or planes simultaneously. So the solution set of a system is precisely the intersection of all its lines or planes. Picture two lines in the plane. Usually they cross at exactly one point, that is the typical case, one unique solution. But two other things can happen. The lines might be parallel, marching alongside each other and never meeting, in which case there is no solution at all. Or the two equations might secretly describe the very same line, lying right on top of one another, so every point on that line is a solution, and there are infinitely many. Those three pictures are the whole story. This leads to one of the most important facts in the subject. A system of linear equations always has exactly one of three outcomes: no solution, one solution, or infinitely many solutions. It can never have, say, two solutions or 5. Why is that? Suppose you found two different solutions, call them P and Q. Because every equation is linear, any blended point along the straight line between P and Q, written as 1 minus t times P plus t times Q, also satisfies the system for every value of t. So the instant you have two distinct solutions, you are forced into infinitely many. That is why 2 is impossible. It would generate a whole line of solutions. The vocabulary we use is this. A system that has at least one solution is called consistent. A system with no solution at all is called inconsistent. Keep those words handy, because deciding whether a system is consistent and then counting its solutions is the main job of the techniques we are about to build. Writing out a system equation by equation is clumsy, so we package it. Take a system of 3 equations and 3 unknowns x, y, and z. Separate it into 3 pieces. First, the coefficients. Lay them out in a grid, 1 row per equation and 1 column per unknown. That grid is the coefficient matrix, which we call A. Second, the unknowns. Stack x, y, and z into a column vector, which we call x. Third, the right-hand sides. Stack the 3 constants into a column vector, which we call b. Now here is the elegant payoff. The entire system collapses into the single statement A times x equals b. The rule for multiplying the matrix A by the vector x is built so that the first row of the product reproduces the first equation exactly, the second row reproduces the second equation, and so on. So this one compact matrix equation says precisely the same thing as the original 3 equations, just packaged for the machinery to come. It is worth seeing 2 ways to read the product A times x, because both matter later. The first is the row view. The ith entry of A times x is the ith row of A dotted with the vector x, that is, the coefficients in that row, each multiplied by its unknown and summed. So every row of the product hands you back one equation. That is the view that makes A times x equals b just a restatement of the system. The second is the column view, and it is deeper. The product A times x is also a linear combination of the columns of A, where the weights are the components of x, x1 times the first column, plus x2 times the second column, and so on. Read this way, the equation A times x equals b is asking a question: what weights on the columns of A combine to produce the vector b? Solving a linear system is the same as expressing B as a combination of the columns of A. That column view will become the heart of how we think about matrices. For the purpose of solving, even the variable names are excess baggage. The letters x, y, and z only tell us which column a coefficient belongs to, and the grid already records that, so we strip the names and keep just the numbers, forming the augmented matrix. We take the coefficient matrix A and glue the right-hand side vector B onto it as one extra column on the right. A vertical bar separates the coefficients from the constants, purely as a bookkeeping reminder of where the equal signs used to be. Now read it back. Each row of this augmented matrix is one full equation. The columns to the left of the bar hold the coefficients of x, y, and z, and the single column to the right holds the constants. Nothing has been lost. The augmented matrix carries the entire system in pure numerical form. This compact grid is the workspace we will operate on next episode, when we start transforming it row by row to extract the solution. Here are the three possibilities drawn side by side for the simplest case of two lines in the plane. In the left panel, the two lines have different slopes, so they slant across each other and cross at exactly one point. That single gold dot is the unique solution, the one pair of numbers that satisfies both equations. In the middle panel, the two lines have the same slope but sit at different heights. They are parallel, running forever side by side and never touching. There is no point on both lines, so the system has no solution, it is inconsistent. In the right panel, the two equations secretly describe the very same line, drawn here twice so you can see they lie exactly on top of each other. Every single point on that line satisfies both equations, so there are infinitely many solutions, all highlighted in gold. 1 point, no points, or a whole line of points. Those three pictures are every linear system there is. The same logic climbs into 3 dimensions, where each equation is a plane instead of a line. On the left, 3 planes tilted at different angles all pass through one common point, the gold dot where all 3 sheets meet. That point is the unique solution of the 3-equation system. The geometry is richer here, though. On the right, look at 3 planes arranged like the 3 sides of a triangular tube. Each pair of planes meets along the line, so there are 3 lines of intersection. But those 3 lines run parallel and never share a common point. No single point lies on all 3 planes at once, so this system has no solution. There are still more arrangements possible. 3 planes can share a whole line, giving infinitely many solutions, or all coincide. But the punchline never changes, even in space. The count of solutions is always 0, 1, or infinitely many. The geometry gets fancier, the rule holds firm. Let's solve a concrete system. We have 2x plus y equals 5 and x minus y equals 1. A quick trick, add the 2 equations together. The plus y in the first and the minus y in the second cancel, leaving 2x plus x, which is 3x, equal to 5 plus 1, which is 6. So 3x equals 6, giving x equals 2. Now back, substitute. Put x equals 2 into the second equation, x minus y equals 1, that is 2 minus y equals 1, so y equals 1. The solution is the pair x equals 2, y equals 1. Let's verify it against both original equations. 2 times 2 plus 1 is 4 plus 1, which is 5. The first equation checks. And 2 minus 1 is 1. The second checks. Geometrically, these were 2 lines with different slopes, so they crossed at exactly one point, and that point is 2, 1. A unique, consistent solution. Now the other 2 outcomes. Start with part A. We have x plus 2y equals 3 and x plus 2y equals 5. Subtract the first from the second. The left sides are identical, so they cancel completely, leaving 0 equals 2. That is false, a flat contradiction. There is no pair of numbers that can make it true, so the system has no solution. Geometrically, these are 2 lines with the same slope but different intercepts, parallel, never meeting. This is an inconsistent system. Now part B. We have x plus 2, y equals 3, and 2x plus 4, y equals 6. Look closely, the second equation is just the first multiplied by 2. They are the same line written twice. So every point on that line solves the system, and there are infinitely many. To describe them all, let y be a free parameter t, and solve the first equation for x equals 3 minus 2t. So the solutions are the pairs 3 minus 2t, comma t, as t ranges over all real numbers. A whole line of solutions captured by one parameter. Let's practice the packaging that powers the rest of the course. Here is a system of 3 equations and 3 unknowns, x, y, and z. Watch the missing variables. The second equation, 2x minus z equals 1, has no y term, so its y coefficient is 0. The third equation, 3y plus 2z equals 7, has no x term, so its x coefficient is 0. Now build the matrix form. The coefficient matrix A has rows 1, 2, 1, then 2, 0, -1, then 0, 3, 2, those zeros standing in for the absent variables. The unknown vector x stacks x, y, z, and the right-hand side vector b stacks 4, 1, 7. So the system is A times x equals b. Finally, drop the variable names and form the augmented matrix, the same coefficient grid with the constants, 4, 1, 7 attached as a fourth column past the vertical bar. That tidy array of numbers is everything the system contains, ready to be solved by elimination. Solving linear systems is one of the oldest computational ideas we have. Around 200 BCE, the Chinese mathematical classic known as the 9 Chapters on the Mathematical Art laid out systems of equations on a counting board and solved them by manipulating the array of numbers, essentially the row reduction we will learn next episode, more than 2,000 years early. Jumping ahead, in 1693, Gottfried Leibniz introduced determinants as a tool for solving linear systems. In the early 1800s, Carl Friedrich Gauss systematized the method of elimination while computing the orbit of an asteroid and surveying the Kingdom of Hanover, which is why we now call it Gaussian elimination. And in 1858, Arthur Cayley took the decisive step of treating the matrix itself as an object with its own algebra, not just a bookkeeping grid. The compact statement, A times x equals b, that we wrote today is the modern endpoint of a 2,000-year story. Let's recap. A linear equation is a sum of constants times unknowns set equal to a number with no squares, no products of unknowns, nothing curved. Geometrically, each equation is a line in the plane or a plane in space, and the solutions of a system are exactly the points where all those lines or planes intersect. From that picture comes the central fact. A linear system has 0, 1, or infinitely many solutions and nothing else. We call a system consistent if it has at least one solution and inconsistent if it has none. We package a whole system into the single equation, A times x equals b, where A holds the coefficients, x holds the unknowns, and b holds the constants, and reading A times x by columns shows that solving the system means writing b as a combination of A's columns. Finally, dropping the variable names gives the augmented matrix the coefficients with the right-hand side attached. Next episode, we take that augmented matrix and run Gaussian elimination, the systematic procedure that cracks any linear system. Today, we met systems of linear equations. A linear equation is a sum of constants times unknowns, set equal to a number, no powers, no products of the variables, nothing curved. A system is a collection of these equations that we ask to hold all at once. Geometrically, each equation in 2 unknowns is a line, and each equation in 3 unknowns is a plane, so solving a system means finding where those lines or planes intersect. From that picture comes the central fact. A linear system has exactly 0, 1, or infinitely many solutions, and never any other number. 2 lines either cross once, run parallel and never meet, or coincide and overlap everywhere. We then learn to package a system compactly. The coefficients form a matrix called A, the unknowns stack into a vector called x, and the right-hand side stack into a vector called b. The whole system becomes the single statement A times x equals b. And if we drop the variable names entirely and just keep the numbers, we get the augmented matrix, the coefficient matrix with the right-hand side attached as one extra column. Next episode, we put that augmented matrix to work with Gaussian elimination, the systematic procedure that solves any system at all. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.